All right. All right. So now we are on like the energy bar charts. So hopefully this will help to make sense of how the kinetic and potential energy kind of stays the same. Like we talked about earlier, the sum of those, should always add up to what it was initially. So it should remain constant. So this is showing you this ball with the initial potential energy being 0 because it's basically on the ground. But it has this velocity vector that's coming off of it. So it's showing you that it's got, this big amount of velocity. So it basically has 0 potential energy, which is shown here on this chart, and all of its kinetic energy. Well, here on the second picture, you're about halfway. So it's got half the kinetic and half the potential, which adds up to be what this total kinetic energy would have been. And then it goes on and it shows at the very top height where it's like that example before with the pebble, at that very top point, it's got 0 velocity. So it's got 0 kinetic energy. And so these basically have flipped. And then again with the half and half, and then it goes back to, the initial where it was just all kinetic energy and 0 potential. Okay, so we got another example here. Dropping a watermelon. So this says that a 5-kilogram watermelon is dropped from a 3rd-story balcony, which is 11 meters above the street. Unfortunately, the water department forgot to replace the cover on a manhole, and the watermelon falls into a 3-meter deep hole. How fast is the watermelon going when it hits the bottom? Okay, so let's write down what we have. Let's go over here to this other slide if you have it printed off. Let's write what we've got. We've got a watermelon that's 5 kilograms. Okay, and it's dropped from a 3rd story, which it says that the height was 11 meters. But then it goes on and it says that it goes an additional how many meters? It goes an additional 3 meters. Okay. So we end up having to figure out like what the velocity is as it hits the very, very bottom. All right, so whenever you go to set this up, you got to use your conservation of energy equation. Kind of figure out which one has what. So does it have final kinetic energy? Yes. Why? Because that's what we're solving for, what the final velocity is, right? Does it have final potential energy? No, because it hits the bottom of the ground, so it's at 0 height. Does it have initial kinetic energy? You're holding a watermelon up on the top of the balcony. So no kinetic energy, but it does have potential. All right, so write out your equations here. Okay, and so you're going to solve for the velocity. So multiply both sides by 2. That's what I would do. So that gets rid of that. Then you're going to divide both sides by m. Gets rid of the mass. And then you're going to have to do the square root. So 2 times gravity times y. Okay? So we have the square root of 2 times 9.8 times the height, which was 11 plus 3. So we end up with 14 here, meters. Whenever you go to do that, you end up with, I think, 17 meters per second. Might make sure on that. But anyway, you want to make sure that when you're doing these that you're adding all of the heights, okay? So, or you're subtracting if that's the case as well. All right, so let's go over to the next slide here. We've got gravitational potential energy still, and we are looking at this figure that is showing a particle that's moving at an angle while it's acted on by gravity. Okay, So remember, in a case like this, work was equal to force times distance, okay? And we have a gravity that is happening in the x direction here. This is showing, this right here is showing the y direction. And we have a displacement in both the x and the y direction, okay? So we end up with our negative mass times gravity because, gravity is only happening in the y direction. This is 0, right? So that's why this ends up being 0. And our displacement is the change of y, okay? So because the force of gravity has no x component, the work depends only on the vertical displacement. Okay, it has to be going in the same direction, parallel to whatever force you are applying to it. Okay, and that's basically what it's stating in this, that the change in gravitational potential energy only depends on the vertical displacement. Okay. So this is saying, starting from rest, a marble first rolls down a steeper hill, then down a less steep hill, for which is going faster at the bottom. And this is showing you that if you're saying that you can set up kinetic energy equal to potential energy, remember, kinetic and potential energy are being set up equal to each other on that longer equation where it says, like this. Like that. Does this have final potential energy once it reaches the bottom? No. Does it have initial kinetic energy at the top? No. So we're saying that the final potential energy is equal to the initial potential energy. Well, is this the same height right here? Yes. Does it have the same mass? Yes. So what should that tell you about the speed here? Like if I did this, if I wrote it all out like this, and I'm looking for the speed here, I'm going to end up getting the square root of 2 times gravity times the height. Well, did the height change? No, it went from this point to this point. Okay? This point to this point. Now, did it maybe, did it take longer or anything like that? That could be an issue, but did it go the same height? It went the same y value. It has the same gravity. So the velocity at the bottom of both of those hills should be the same. Okay? According to conservation of energy, that is going to prove that those are both the same. So gravitational potential energy, this is showing you that what happens if you have friction or frictionless and things like that. So this figure is showing an object that's sliding down a curved frictionless surface, right? And that if it's at a slope, then our normal force is perpendicular to the surface, and that the gravitational force is straight down no matter what. So the change in the gravitational potential energy of the object and the earth depends on, again, this change of y value, okay? Because that is what is affecting potential energy. The distance of the object descends, not the shape of the curve. So the normal force is always perpendicular, and which we just discussed, and so that is saying that that it's doing that, so it does no work, okay, for that normal force there. Okay. So basically it just depends on at this point right here to this bottom point right here. It depends on the change of the y. Okay. So this one is saying, what is like a small child slides down the 4 frictionless sides. Rank in order from the largest to smallest her speeds at the bottom. Okay. Again, what is the only thing that is affecting the potential energy here? The only thing that's affecting the potential energy is the height, Does the height change in any of these? No. So theoretically, then the velocity on these should be what? They should be equal because, again, your kinetic is equal to your potential energy. Okay? So now let's do another example. This is saying the speed of a sled. So Christine runs forward with her sled at 2 meters per second. She hops onto the sled at the top of a 5 meter high, very slippery slope. What is her speed at the bottom? All right, so I'm going to write this stuff down over here. First off, her initial speed that she's got going here is 2 meters per second. And she hops on at the top of a hill, which is at 5 meters. And it's a very slippery slope. So basically there is hardly any friction. At least they're not going to, they don't want that information apparently. So they're wanting you to figure out what the final velocity is. Okay? So we're going to use our equation again. Oh, I wrote that wrong. I don't know why I wrote equals there. Okay, so we've got our final kinetic energy plus our final potential energy is equal to our initial kinetic energy plus our initial potential energy. All right, so let's write all this. Well, let's figure out which one actually cancels out, I guess. So do we have final kinetic energy? Well, I hope so, because that's what we're looking for, right? We're looking for the final velocity. Do we have final potential energy? Well, it says what's her speed at the bottom. So our potential energy at the bottom should be 0, right? Do we have initial kinetic energy? Well, we should, because we had initial velocity. And then do we have initial potential energy? Yes, we do. So we set these up. See, this is one where we haven't had like this before because we've always canceled out 2 of them. All right, so now what are we trying to solve for? We're trying to solve for the final velocity. So we're going to move everything over in order to do that. So first, let's multiply both sides by 2, which gets rid of that. And it gets rid of this too. So we end up with mv squared plus 2mgy. And we're going to divide both sides by m. It's going to cancel all of that out. And you're going to end up having to do the square root. Excuse me. So we're going to have 2 meters per second squared plus 2 times 9.8 times that 5. Okay, do the square root of all of that, and you should get 10 meters per second. All right, so there's an example where you would have, some initial kinetic energy and initial potential energy, and you still have to find something from the other side. All right, so I'm going to stop the video there, and I'll start up